This problem is asking us to find the initial molarity of ammonia in an ammonia solution with a pH of 11.17. This is very similar to the problem that we just worked, but in reverse. We're given the pH and we're asked to go backwards to the initial molarity, whereas in the previous problem we were given that initial molarity and asked to find the pH. It's the same reaction. It'll be ammonia plus water in equilibrium with the ammonium ion plus the hydroxide ion. Again, water is a pure liquid, so as we're looking to fill out values for our initial, our change, and our equilibrium, water can just go in as a squiggle. Let's see, we're looking for ammonia's initial concentration. I'm just going to call that B naught. Right? We don't know what that number is yet. B is base. So this is our initial base concentration. Initially, we just dissolve the base in water. So initially, the concentrations of ammonium and hydroxide are 0. To reach equilibrium, since Q is equal to 0, this has to go in the forward direction, and so that means we're going to lose some of our reactants, and we're going to gain some of our products. Everybody has a coefficient of 1, so they're all 1s here. And then at equilibrium, we're going to have B naught minus X, X, and X. Now, from the data we were given in the problem, and from our standard assumption, we can simplify our equilibrium line a little bit. For the ammonia concentration, let's assume that, ooh, that was really ugly writing. Let's assume that X is very small compared to our initial base concentration. When we make that assumption, then the concentration of B naught minus X really becomes just B naught. So our equilibrium line simplifies down to be just B naught. We can ignore the minus X. And then we were given the pH. From the pH, we can figure out what the equilibrium concentration of hydroxide is, and that will give us a value for X. So there's one extra step involved in there. If the pH is equal to 11.17 and we want to get to the hydroxide ion molarity, we're going to have to go through either the hydrogen ion molarity or POH. I prefer doing this through POH. So POH will be 14 minus pH. So 14 minus 11.17 gives us 2.83. Well, if POH is 2.83, then the hydroxide ion concentration will be 10 to the minus 2.83, which gives us a value of 1. Let's see. I should only keep 2 significant figures, but I don't want to get into cumulative rounding errors. So I'm going to keep an extra sig fig and make this 1.48. I'll round appropriately at the very end. All right, so 1.48 times 10 to the minus 3 for our hydroxide ion concentration. And then let's take a look at our K expression. Our K expression says that this will be the concentration of ammonium ion times the concentration of hydroxide ion, all divided by the concentration of ammonia. And again, these values all have to come from the E line, the equilibrium line of our chart. K is 1.8 times 10 to the minus 5. The ammonium ion and hydroxide ion are both X, but we also found that that was equal to 1.48 times 10 to the minus 3. So I'll plug that in on the top, 1.48 times 10 to the minus 3, and that'll be squared because it's the same thing for both ammonium and hydroxide. And then all of that will be divided by our initial base concentration. Solving for variables in the denominator often causes problems, so the first thing I do when I see one down there is I get it to the numerator as quickly as I can. So to move B naught out of the denominator, let's multiply both sides by B naught. That'll cancel out on the right-hand side, and that'll leave me with 1.8 times 10 to the negative 5, all multiplied times B naught on the left-hand side, and that'll be equal to 1.48 times 10 to the negative 3 quantity squared over there on the right-hand side. If I solve that expression for B naught, what I'll need to do is divide both sides by 1.8 times 10 to the minus 5. So writing this all one more time, 1.48 times 10 to the negative 3 squared, and all divided by 1.8 times 10 to the negative 5. That will give us a number for B naught. So let me run that through my calculator. I've got the 1.48 times 10 to the negative 3 already showing. So now I'm going to square that and divide by 1.8 times 10 to the negative 5. And that gives me a value of 0.12 molar. I'm really limited to two significant figures here in my molarity because our pH originally had 2 decimal places and our K value has 2 sig figs, so both of those point to 2 significant figures in our base molarity. There we go, final answer. The initial concentration of ammonia is 0.12 molar. With this video, we wrapped up our equilibrium calculations for weak acids and weak bases. Both of these types of chemicals have equilibria that get established, and then we use the numerical value for the equilibrium constant to help calculate whatever we're looking for. The weak base equilibria sometimes have some extra steps involved. You have to include water in the equilibrium reaction. And often, since we specify things in terms of pH all of the time, you have to remember that the weak base expression involves hydroxide ion, so there's an extra step in going from pH to the molarity of the hydroxide ion, either going through pOH or calculating the hydrogen ion concentration from the pH. Either way will work.